the next step we are going to start graphing rational functions. We have lots of components that are going to go into this, just like when we graphed polynomials, we didn't just jump in and start graphing them right away. We talked about a lot of their properties first. When I talk about a rational function, I just mean when you are dividing two polynomials. So we've graphed individual polynomials, now we're going to look at what happens when we divide those. We'll talk a lot about the domain. We know if you have a fraction, what's the one thing that can't happen? What's the one? Okay, the bottom can't be 0 when we are working with these. So those places that make the bottom 0 are where our graph is going to do funny things. So the first piece, we're just going to look at these and find our domain. We're basically figuring out what x can't be. So when I look at this, I'm only looking at the bottom. And when I find the domain, I know that the bottom cannot be 0. So on this one, x cannot be -5. In interval notation, that's everything except -5. So it's everything smaller than that and everything bigger than that. Right. On B, what would we have to do? So the bottom, x squared minus 4, can't be 0, so x squared can't be 2. Square root plus and minus, so x can't be, oh my goodness. See, I told you, when we added this 4 over, that should have been a 4 there, and the square root of 4 is 2. I've been doing this stuff all day. I'm not with it. So x can't be positive or -2. Typically, what I'm going to do, if it's more than one x value that you can't equal, I will allow you to leave it like this. The interval notation, if you think about that, it's everything except these numbers. So it's everything smaller than -2, everything in between -2 and 2, and everything bigger than 2. But for me, if it's just one value, I want the interval. If it's more than one value, you can just say x cannot equal this. Bless you. All right. For C. What? We said we have a fraction. We know the bottom can't be 0.
So x squared.
What kind of number do we get?
Mm-hmm.
When we graph imaginary, or when we graph, do we have to worry about imaginary numbers?
No.
So if the only thing x can't be is imaginary, your domain is negative infinity to positive infinity. You can plug in any x value we want. D. If we say the bottom can't be 0, does 3 ever equal 0?
No.
So what's my domain? E. Right. X minus 1 can't be 0, so x can't be 1. How would I write that in interval notation? Are we okay with domains? Something that I want to mention, this last one. Okay, we just did the domain, we said it couldn't be 1. If I factor the top, how does x squared minus 1 factor? Those x minus 1s end up canceling and you get x plus 1. But what would be the domain of x plus 1? Negative infinity to positive infinity because there's no fraction. Technically, the graphs of these are different because the domains are different. As far as simplifying, they turn out to be the same. But when we deal with these graphs, we are going to have to look at the original functions when we determine our domain. So domain is based off the original, not what it might simplify into. So that's why I wasn't trying to factor and cancel anything with the domain. I just went straight to looking at the bottom. Now, when we graph these rational functions, the things that make the bottom equal 0 are going to create what are called asymptotes on the graph. Asymptotes are lines that we are getting closer to, but not actually hitting. There's 3 types of asymptotes: horizontal, so just a horizontal line; vertical. The third is oblique, that's just any other line. So just a slanted line, sometimes those are called slant asymptotes. And we will be talking about these throughout the entire chapter. Today, we are only going to focus on graphing 2 specific rational functions. And we will use these 2 starting points and some transformations to graph them. So the first one, and you might want to write this down because there might be some questions on the Math Excel where all you have to do is type in some of the pieces we write down on this. The reciprocal function, 1 over x.
X over.
Okay, so yeah, the reciprocal of that would be x over 1. The name of this is technically the reciprocal because it's just taking the reciprocal of x. If we wanted to graph it, let's plug in some points. What happens if you put in 1? What's 1 over 1?
1.
Okay, if we put in 2, what's 1 over 2?
2.
1 divided by 2?
That's 1/2.
If we put in 3, what do we get? 1/3. This is just getting smaller, isn't it? Can you do 1 divided by something and get 0 for an answer? No. Okay, what happens if I put in 1/2? What's 1 divided by 1/2? 1 divided by 1/3 is 3. Can you plug in 0?
Yeah.
Can we do 1 divided by 0?
No.
No. So this part is actually looking like this. It's not hitting the axes because we don't get 0. Let's put in some negatives. So 1 divided by -1 is -1. 1 divided by -2 is -1/2. 1 divided by -3 is -1/3. It looks the exact same, except negative. So it's just these 2 little curves. What's the domain for this graph? You get 2 places. If I look at the original, what's the one thing x it can't be? 0. When I look at my graph, it comes from negative infinity, it stops at 0, picks up again after that.
So negative infinity is 0,
My range, if I look at my y values, we have all the negatives, we have all the positives, but what don't we hit?
0.
0, so it's the same thing. Okay. So this graph has a vertical asymptote. A vertical asymptote is a vertical line that we get close to and don't actually touch. We usually draw those as dashed lines. It's just the y-axis. The equation of a vertical line is always x equals a number. In this case, it's x equals 0. So it's that one thing that it couldn't be in the domain. That's where we get a vertical asymptote. Horizontal asymptote. What's the horizontal line we're getting close to?
X, so 0.
So horizontal lines are y equals, so y equals 0. And I don't want to talk about even and odd today, so we're just going to skip that for now. All right. Questions there? When we use transformations with these functions, our asymptotes are going to get moved as well. So if I wanted to graph 1 over x plus 1, okay. we could think about parent functions. We know 1 over x, we are not going to be very precise with these graphs. 1 over x looks like this, right? If you add 1 to your x, what does that do to your graph?
It makes it go left.
It would go left 1. So what's the one number we can't plug in now?
Negative
-1. So if I drew this, my vertical asymptote is at -1 because my whole graph moved left 1. Did the horizontal asymptote move? Did we move up or down at all?
No.
No. So on these, unlike most of the others where I made you give me fairly exact graphs when we did transformations, just make sure your asymptotes are in the right spots and then draw in your curves. So it's just going to look like this. Like this. What I'm focused on more today is those asymptotes than anything else. So, can you tell me the domain of this graph?
Negative infinity, -1 to infinity, -1 plus infinity.
We can get that from looking at the graph we just drew or from the original equation. We know the bottom can't be 0, so that's the only thing that we can't have. Normally, with these, our parent function, the range is -infinity to 0, union 0 to infinity. If you don't move it up or down, that isn't going to change. And we can see that's the same thing. We had a horizontal asymptote at 0, so the range stayed the same. So vertical and horizontal asymptotes. With our asymptotes, they are lines, so you have to give just a full equation. You can't just say -1. Vertical is always x equals a number. Horizontal is y equals. So what's my vertical asymptote? And my horizontal?
0.
So vertical x equals -1, horizontal y equals 0. Questions here? So when you move your graph left and right, it will move your vertical asymptote with it. What do you think would happen if we moved up or down?
Horizontal.
It's going to move our horizontal. Okay, so let's try that. So my parent function is this 1 over x, and we know 1 over x kind of looks like this.
Wouldn't that flip it?
Yeah, there's a -1 over x, so that would flip our graph. So it's going to start up here, move down here. And what's this -2 do?
Makes it go down.
Move down.
Down.
Yeah, minus goes down. So we need to flip and go down. So which asymptote gets moved?
The one.
Yeah, the y equals 1, the horizontal one. So it went down to, the only way the vertical asymptote moves is if you go left or right. We didn't, so my vertical is still on the axis. Okay, my graph is normally like we drew up here, but the negative flips it, so this piece is above, and this one is below. Remember, those lines, we need to be getting closer to them, but we don't actually hit them. We're just approaching.
This is what all the reciprocal functions do.
Mm-hmm. So what's our domain? But the range would be
-2.
-infinity to -2. Union -2 to infinity. What's my vertical asymptote?
X equals 0.
And my horizontal?
Y equals 0.
So far, so good? Almost done, just a couple more pieces. The second parent function that I wanted to touch on today is the reciprocal square function. And it's going to look basically the same, except if you square something, will you have any negatives? No. So we still can't plug in 0, so we would still have a vertical asymptote at 0. If you put in 1, what's 1 over 1 squared? So 1, 1 is still on here. If I put in 2, what's 1 over 2 squared? 1/4. So it's just getting smaller a little faster. If you put in 1/2, what would you get out?
Wouldn't it just be
4, because 1/2 squared is 1/4, so 1 over 1/4. So it's got the same general shape, just a little steeper. But what happens if I plug in -1?
It'd just be
It would be 1. This one actually looks the same on both sides, because when you square a negative, it becomes positive. So my vertical is still at 0, and my horizontal is actually at 0 as well. So domain and range, we can look at our graph. What's my domain? Union, search infinity. What's my range?
no, it's
It's different because we don't have any negatives.
0.
So it's just the 0 to infinity. Vertical asymptote?
X equals
And horizontal?
Y.
And like I said, I want to skip even and odd for now. We'll touch on that later on in the chapter. Okay, so let's practice graphing a transformation of this. All right. So my parent function, yeah, it's 1 over, you guys with me? The x squared, so it's the one where both ends are going up.
It's just
Can you guys tell me without graphing that what the vertical and horizontal asymptotes would be?
it'd be 2 and negative.
X equals 0, y equals 0.
Normally it's x equals 0 and y equals 0, right? What does this minus 2 do to my graph?
Makes it go right.
We go right 2. So where does my vertical move to?
2.
Positive 2. So vertical asymptote would be at x equals 2.
And then horizontal would be Y equals negative. She asked what it was. She asked what it was.
So we're going right 2. And minus 4 would go down 4. So the horizontal moves down to negative 4. So on some of your homework questions, it asks you for your asymptotes. You don't even have to draw the graph if all we need are the asymptotes. Just think about how they would move. And then we know the graph for this is both ends going up. What's the domain?
Negative infinity to positive infinity. Range is negative root negative 4. Or no, negative 4 to infinity.
We start at negative 4 and keep going up. So negative 4 to positive infinity will be our range. All right. I just want to show you a graph and ask if you can identify a few pieces, and then I'm done. So, I didn't draw in the asymptotes. Can we put them on here?
Yes.
Where would our vertical go? So that means my domain is everything except 2. So negative infinity to 2 and 2 to infinity. And we can go ahead and say the vertical asymptote. How would I write that?
X equals.
Okay, where is my horizontal asymptote?
Positive 1.
Okay, it's that breaking point of my graphs. So my range is everything except 1. So negative infinity to 1, and 1 to infinity. Horizontal asymptote is
Y equals.
y equals. X-intercept. Where does this graph hit the x-axis? 1. Y-intercept. Where does it hit the y-axis? 1. Yeah. We haven't seen any oblique asymptotes yet. That would be like a dashed line or a like slanted line we're getting close to. There isn't one here. We'll be looking at that more next week, but we haven't seen any yet. So there are 9 questions on your Math Excel, and you've got